Good afternoon, everyone. My name is Zhen. Today I will present our work cover finding important parameters for storage systems. This is a joint work between Stony Brook University and Harvey College. This is an outline of my presentation. I will first provide a general introduction to our work, including its motivation and our key contributions. Followed by that, I will explain some of the background knowledge of this project. Then I will talk about the design of cover in detail. I will explain how we evaluate cover thoroughly and present some of our evaluation results. I will then briefly discuss related work and conclude with the discussion on some of our future work. Storage systems are critical components of modern computer systems that have significant impact on application performance and efficiency. They often come with a large number of configurable parameters that control and affect their overall behavior. Our previous research have shown that tuning storage system parameters can improve system performance significantly. To deal with a large number of possible storage configurations, there are two tracks of efforts. System administrators usually focus on their domain expertise to tune a few frequently used and well-studied parameters that are believed to significantly impact system performance. Recently, research has been done on applying various types of auto-tuning or machine learning algorithms on storage systems and show some exciting results. However, we believe the problem of tuning storage system is far from being solved. On one hand, when storage systems come with hundreds of parameters, both manual and auto-tuning are known to have scalability issues in higher dimensions. On the other hand, evaluating a single storage configuration is time-consuming, which requires the tuning methodology to be extremely efficient. Motivated by these facts and challenges, this work is a continuation of our previous efforts on auto-tuning storage systems. Our previous study has observed that certain storage parameters have greater impact on system performance than the others. So if we can eliminate less important parameters and order parameters by their importance, the number of configurations that needed to be considered either by humans or algorithms can be reduced significantly. So in this work, we took the first step towards this and proposed cover, which aims at analyzing and selecting parameters by their impact. Cover consists of three components. It first proposes a measurement to quantify and compare the impact of different parameters' impact on predefined objectives, such as latency or throughput. And the parameters' importance can depend on specific hardware and workload. And also evaluating a single storage configuration is time-consuming. So Cover's parameter selection algorithm will have to make decisions by evaluating only a small number of storage configurations. Therefore, Cover includes a sampling method, which is able to pick a small number of configurations representing the whole parameter space. Based on this, Cover proposed a greedy algorithm to select important parameters for storage systems. The key contributions of our work can be summarized as follows. We provided a sort of quantitative analysis on the impact of storage system parameters for 7 different file systems and across 4 different workloads. We proposed Cover, which used a variance-based metric for storage parameter importance and a sampling method to drive a greedy algorithm that can select important parameters for storage systems with only a small number of evaluations. We thoroughly evaluated Cover's ability to identify important parameters in terms of I/O throughput and the latency. Cover was able to identify the near optimal set of important parameters in all cases. Next, I will cover some background knowledge of our work. Here, I'd like to first define several terms which will be frequently used during this presentation. In this work, we use storage systems to refer file systems, the underlying storage devices, and any layers between them. Storage systems usually come with many configure options we call each of them as one parameter. For example, block size is a common parameter in many file systems. Each parameter can be assigned with predefined parameter values. For example, block size for X4 can take values of 1K, 2K, and 4K. A configuration is defined as a certain combination of parameter values. For example, the configuration here is one configuration with 3 parameters. And all possible configurations form a parameter space. Several characteristics of storage systems actually lead to the following challenges for tuning storage systems and therefore for storage system parameter selection. Many storage systems come with huge parameter spaces. For example, X4 has around 60 parameters, which results in around 10 to the power of 37 unique configurations. And storage systems have expanded from one of few nodes to distributed large-scale environments. Evaluating a single storage configuration is often time-consuming, taking from minutes to hours of time. And the storage evaluation result depends on the specific environment, includes the hardware, software, and the workload. An important parameter in one environment might become less important when the environment changes. Many storage parameters take discrete or non-numeric values. For example, Linux I/O scheduler can take on these 3 values. As mentioned just now, both manual and auto-tuning for storage systems had difficulty in scaling into high-dimensional spaces, which leads us to explore the possibility of dimensionality reduction. In general, dimensionality reduction techniques can be divided into 2 categories. Feature extraction refers to projecting high-dimensional data into low-dimensional spaces. The newly constructed features or parameters are usually linear or non-linear combinations of the original ones. One major drawback of feature extraction is that the physical meaning of each feature is lost by the projection. The other type of techniques is feature selection, which directly selects a subset of features from the original ones. They are either based on the relationship between parameters or the relationship between parameter and the target variable. In our case, it's a throughput or I/O latency. For storage systems, we believe the latter fits our needs better. For example, we are less interested in the relationship between the block size and the inode size of a file system. We are more interested in the impact of block size values on the system's throughput. Next, I will talk about the design details of Carver. For the purpose of parameter selection, we first need a suitable measurement for storage parameter importance. Many storage parameters are categorical, while the target variable, which in our case is the system throughput or I/O latency, is often continuous. We therefore decided to use the reduction in variance to measure parameter importance. Similar metrics have been applied in some regression trees. Intuitively, an important parameter should divide a set of configurations into multiple subsets, and the weighted sum of variance within each subset should be much smaller than the variance of the original set. We have the formal definition in our paper. We define the conditional parameter importance as the importance of one parameter with the value of another parameter fixed. Given the large parameter space and the time needed to evaluate a single storage configurations, we must limit the number of experimental runs required for selecting important parameters. Therefore, Carver needs a sampling method that can cover this space uniformly and comprehensively. We decided to apply Latin hypercube sampling in 2 dimensions, a square grid containing samples in a Latin square if there is only one sample in each row and in each column. And this definition can be generalized into higher dimensions. Latin hypercube sampling has proved to be useful in many types of system analysis. Next, I will briefly explain how Carver's selection algorithm works in a visualized way. We have the formal pseudocode in our paper. First, a set of evaluation results is given as the input. This can either be the evaluation results of the whole parameter space or evaluating only a set of small number of configurations picked by Carver's sampling method. For the most important parameter, Carver calculates the parameter importance for each parameter, which is defined as the reduction invariance, and selects the parameter with the highest reduction invariance as the most important one. Let's assume in the previous step, Carver picks x1 as the most important parameter. Then Carver calculates the conditional parameter importance for each remaining parameter by fixing the value of x1 and chooses the maximum of this as the final conditional parameter importance. For example, for parameter x2, it calculates the conditional parameter importance by fixing x1 to each of its possible values, and then the maximum of this will be the conditional parameter importance of x2 given x1. Carver repeats the same calculation for each remaining parameter, and the one with the largest conditional parameter importance given x1 will be picked as the next important parameter. Carver will repeat the same process until certain stopping criteria has been satisfied. For example, users might be interested in 3 most important parameters. Carver will then stop after selecting the 3rd parameter. Another example of criteria is that if the variance within each subset of configurations by fixing the values of already selected parameters falls below a certain threshold, Carver will just stop. The intuition behind this is that fixing the values of selected parameters already results in a configuration space where all possible configurations have very similar performance. Therefore, there's no need to further select any other parameters. Next, I will talk about our experiment settings and some of our evaluation results. More details can be found in our paper. Our experiments were conducted on servers with 24 gigabytes of RAM and 4 different types of storage devices. We use FileBench to benchmark storage configurations and use the 4 different macro workloads as listed here. In the beginning, we stick with the default working set size provided by FileBench. We refer to this setting as S1. Later, we changed to S2, where we increased the working set size to 10 gigabytes and limited the RAM size to 4 gigabytes, so that the working set size is much larger than the RAM. Our parameter space was selected in collaboration with several storage experts. We chose 7 Linux file systems that span a wide range of designs and features, and several commonly tuned storage parameters. We took the following methodology in our experiments. We pre-collected benchmark results for all possible configurations in our parameter spaces. We repeated each experiment for at least 3 runs to get more representative and stable results. Having the whole dataset allows us to evaluate the ground truth of parameter importance, which will be used to evaluate Carver's ability of selecting important parameters with only a small subset of configurations. Next, I will present some of our evaluation results. This figure here shows the parameter importance evaluated by our proposed measurements. And here is x64 under the file server workload. The y-axis for the top figure is the parameter importance value calculated by Carver. The y-axis on the bottom figure is the conditional parameter importance calculated by fixing the value of the most important one. As we can see, the Juno option is selected as the most important parameter. The reduction in variance of throughputs is actually orders of magnitude larger than all the other parameters. Given that Carver will fix the value of Juno option and calculates the conditional parameter importance for the remaining ones, as shown in the bottom figure. Clearly, the device type is the second most important one. We thoroughly evaluated Carver on multiple on all of our collected datasets, and we show some of the results here. As we can see that the important parameters are quite diverse and depend significantly on the file system type and the workloads. For ext4 under DB server, the top 4 ranked parameters are block size, inode size, IO schedule, and the journal option. When the workload changed to web server, the top 4 parameters becomes inode size, flex block, group size, block size, and the journal option. And for file server, we only found 3 important parameters. This indicates that fixing the values of these 3 parameters already result in quite stable throughput. Note here that for BTRFS under the default web server, we didn't find any important parameters. This is because the web server is a workload consisting mostly of read operations, and the default working set size provided by file bench is very small. So all BTRFS configurations actually produce quite similar throughput values under this workload. Here we further evaluate cover only a small fraction of the dataset with the help of Latin Hypercube sampling. The bottom x-axis shows the percentage of the whole dataset that were used by cover, and it is in log scale. The top axis shows the estimated running time for evaluation. In our experiments, one benchmark run with default file bench workload takes around 100 seconds. Here we repeated the same experiments for 1,000 runs to measure cover's ability to select parameters. The y-axis shows the fraction of runs that successfully found the same important parameter as the ground truth, which were obtained on the complete dataset. Here, the red line represents the most important parameter, and blue line for the second ranked one, and the green line for the third. So as we can see that cover is quite efficient in identifying important parameters, even with 0.1% of the dataset, which is actually around 7 configurations. Cover has around a probability of 60% to correctly identify the most important parameter. And when using 0.4%, cover was able to find the first and the second ranked parameter in nearly all of the 1,000 runs. The chance of correctly selecting the third important parameter increased with the percentage of the dataset used, and with around 1% of the dataset, cover has a probability of around 60% to find the third important parameter. Here we present another evaluation of cover on BTRFS under the default file server workload. The x and the y-axis are the same with, the meanings are the same with previous figure. The ranges of values are different. Under BTRFS, cover needed a larger fraction of the dataset to make correct selections. This is because in our experiment settings, BTRFS only has 288 configurations, compared with more than 6,000 for XT4. Evaluating only around 16% of all BTRFS configurations, cover found the first and the second important parameter with greater than 80% of probability. And the cover identified the third parameter in more than 80% of the runs with 31% of the datasets sampled. Now I will discuss some related work of this project. Several work have been done on analyzing parameter importance for various computer systems. However, they are all not the best fit for storage systems. They either handle categorical parameters poorly or having scalability issues in high dimensional spaces. In our work, we took the first step in selecting important parameters for storage systems and choose a variance-based measurement for parameter importance. In the past few years, several work have been done on auto-tuning storage systems. Many different algorithms have been applied, including genetic algorithms, deep Q networks, and more. Our prior work did a comparative analysis on various types of auto-tuning algorithms, which also leads to and motivates this work. Now I will conclude this presentation and discuss future work of our project. In this work, we proposed Carver for efficiently selecting storage parameters. Carver includes a variance-based measurement for storage parameter importance, a sampling method to drive a greedy algorithm to select parameters efficiently. We provided thorough study of storage parameter importance and demonstrated Carver's efficiency by testing it on small fraction of the configuration spaces. In the future, we plan to extend Carver to explore more parameter selection techniques for storage systems. We will evaluate Carver with more optimization objectives and on larger storage parameter spaces. We plan to extend Carver's parameter selection algorithm into the area of multi-objective optimization. And we plan to integrate Carver with auto-tuning algorithms. That's all for my presentation. Thanks for listening, and I'm ready to take questions.
Thank you very much. So we have a few minutes for the questions. Any questions?
Vasily Tarasov, IBM Research. So I'm just curious, in the multi-tenant setups, right? If you have, we share resources, right? Storage, network, compute, it's all shared. And then if you run a different workload in parallel, it does impact the performance of the other workload in many scenarios. Do you think it also impacts the importance of parameters? So would your result change if you would in parallel run a different workload?
If the mixes of workloads remains the same, then we can treat it as one kind of compound workload, and then the framework would work. But if the mixes change, then it's a different workload.
I see.
I guess that's kind of the future work, how Carver will adapt to the change in workload.
Mm-hmm. Are you concerned that there may be too many combinations of different workloads to, represent each mix as an independent workload? Like, if many tenants run many different workloads, there's so many different combinations that can be there.
Yeah, that's true. Yeah, I guess that's future work.
Mm-hmm. Thank you.
Okay, we have time for a few more questions. Okay, yeah.
Hey, I'm Rohan from Northeastern. I'd like to know how would the performance of Carver vary when the difference between the importance of several parameters is not very much?
Sorry, could you repeat that?
How would the performance of Carver vary when the difference between the importance of several parameters is not very much?
When the difference between parameters are not. So in all the data sets that we collected, there are always a few parameters that are much more important than the others. So it's kind of, so Carver will be able to pick the first, let's say, 3 or 4 important parameters. But after that, let's say all the remaining parameters are not that important, then the stopping criteria will just stop the algorithm because there's no need to select the next one.
Okay, thank you.
right?
Hi, this
Go
is
ahead.
Hal from ByteDance. I have a question. So usually some of the parameters became important only under a certain and sometimes rare to occur workloads. How do you make sure that when you do the sampling, the workload you use covers those kind of rare cases?
Actually, this work, I mentioned that it's a continuation of the auto-tuning work, which is a much bigger project. So in our overall auto-tuning framework, there will be a component that can characterize the workload and identify the workload. So if the workload changes, that can be fitted into the parameter selection part.
I see. So you mean that there's gonna be like a upper layer system that observe a relatively long history of workloads and see which kind of workloads are representative? Is that the case?
Yeah, that's one choice. Basically, that's beyond the scope of this particular paper.
Okay. All right. Thank you.
Hi, this is Zhen from VMware, and I have a question about, so in your presentation, you basically collect all the performance data and then build a performance model, right? So is that possible to make your method running well in online or running workload that building the model with the workload running?
So first, the parameter selection algorithm does not need the whole data set. The whole data set is just for evaluation.
Okay.
And in the evaluation, we sample the data set. For example, we only use maybe 0.1 or 1% of the data set to feed into the algorithm.
Oh, so another question is, so in your test, you are using the file bench, right?
Yeah.
Which is a synthetic workload generator.
Mm-hmm.
Have you tested your algorithm in workload traces or real-world workload?
We haven't done that, but that's part of the future work. We do plan to do that, yes.
Okay, thank you.
All right. Okay, let's thank the speaker again.